So these are really nice. So we're going to set up a couple of useful results, and that may be what we need to do to get us going. So then we'll get to some calculations at the end here. So, okay, so there's a couple of sneaky results, and so we had this kind of very basic, powerful one, which is that the sum of two random variables, the generating function for the sum is the product of the generating functions for the individual variables. Okay, so we're going to do something slightly different. So we're going to have two random variables here, u and v, and again the value is 0, 1, 2. That's the general thing we're doing. Probability distributions will be u sub k and v sub k, and we'll try to use this notation, right? Lots of big capital letters making statements. So here's our third random variable. It's an interesting random variable. This is the one I mentioned the other day. We choose from the u distribution, we get some number from that, and then we go over to the v distribution and select from it that many times, and then add it up. So this is where you roll your 20-sided die, and you get a 17, and then you walk over to a 6-sided die, and you roll that 17 times and add up those numbers. Yeah? So that's sort of a funny thing to do. And I mean, it feels like you should be able to work this out. So it turns out that this has a very nice story for the generating functions, which is that the generating function for this new variable w is the composition of them. Pretty groovy, right? Yeah. This is cool. There's one other sneaky result, which is pretty simple, but we're going to do these sort of two. So it's a beautiful result. It's going to take us a little while to work through it. We're going to slowly get to it. There's another way of proving it, which I like to have in the assignments, which is very nutritious. But this is a groovy thing. But it means that, it's a turducken kind of situation, right? So there's going to be sort of you could make it kind of a nasty function, right? Functions with functions. Yeah. But writing it down like this, it all looks very pleasant and benign. Okay, so and the thing, the use for this will be, we hit a node, we select from the R sub k distribution, which tells us how many other friends a node has, and then we might want to select from the row distribution, which tells us for each of those friends what's probably that those friends are part of a finite component, and so this thing would then add up all those finite component sizes. Right, so this little structure here, and I'll just flick back and I'll come back, is exactly what we want for like this thing, for example. And it's true for the previous slide as well, or the slide that comes before, but right, we're going to sample from this guy here, and that's going to give us, it's going to be about this piece here. We're going to sample from it, it's going to give us k, and then we're going to sample these ones and then add them up. And the added up part is what we want. This is actually this is how many you choose. You roll them all, and then boom, add them up. That little horrible thing? Distributed as. Yeah. So that's yeah. No? Does anyone ever see this? What's the right thing to do in 2018? I mean, so like you might say distributed as, yeah, I'll ask you. Distributed as it's good to put it here so we don't lose it. Boop. Like distributed as, something like, a normal 0, 1. Right? Something like that. So that's completely unnecessary. Yeah, but I did it.
So you have I equals 1 on the bottom of that sign. But U has everything from 0 to up.
That's true. Mm-hmm. So in that case, you would sample from, so that would kill the thing. It means you would have no samples. Yeah. So, because that's okay too, right? So for example, if you go to a node and you sample that it has 0 other friends, I mean, maybe that's a bit clumsily written, but I suppose, but you go to a node, you sample from R sub k, and you get a 0 back. So this is a node that has one friend, which is you. So it has no other friends. So when you say, what's the probability that it is part of a component of whatever, then you're going to get 0 things to add up. You'll always add 1 for it. So when you go out there, you'll get, what's the probability that you'll get a 1 for that one? Yeah. And this sum will just return a 0 because it's 1 to 0, which feels a little wrong. Nice detail. Appreciate it. So making anyone feel nauseous? Okay. Let's see if we can do it. Oh, yeah, look, there's a tarot card for this one. Yeah, see? So much fun. There are 17s on there. Okay, so but that's the idea, right? So you know, add things up. It's a random sum of randomness. I know I've mentioned this, right? But at CMU there used to be a slightly different thing, I guess, but there was a race every year where they had a giant die, and they would someone would throw it out on the track, right? It was hilarious, fun-sized die. So they'd throw it, and that would be the number of laps you had to run, right? So you get a 1 or a 6, right? So this, it's a big variation between 400 and 2400 meters. So you do that, but as soon as the first person finishes whatever that was, they roll it again, and that's how much further you have to run. It's an interesting, right? So it's anywhere between, and we looked at that distribution the other day, right? It's Settlers of Catan with extra pain. Yeah, it's the triangle distribution, right? So 800, it could be an 800, 1 in 36 chance, or it could be a 40, it could be a 5K basically, yeah. You want to do that? Oh, coaches do this all the time, effectively. No, I mean, right, this was a way of kind of making it coaches do this all the time. We're just going to do 4. Maybe 4 more.
Make it unexpected to how hard the workout was
Yeah. Yeah. Absolutely. Yeah. That's all planned out, though. Yeah.
First was. It was some sort of incentive to try and be the first one. Because
even though you knew there was an uncertainty to how much you were going to run.
I think so. Because when I did it in high school, the first person across got to roll the dice.
Oh, I see. Oh, you did do that. Okay, that's interesting. I mean, there's a kettlebell workout where you basically, you roll 2 die, and that's how many minutes you're going to do the thing for. So you adjust. And the whole idea was just to make it more, I mean, it's sort of nerve-wracking too, because you're like, oh my God. When I set up, I had a little app with a thing so I could do it. Okay. All right, let's work through this, and that's where we'll get. No alto playing. And then you can leave. I'll put up a picture of Pratchett. Okay, so let's see if we can do this. We're going to kind of explain. We're going to work our way through it. So the probability that we end up with k from these, right, we're going to sum up. We're going to get a random number to roll, and then we roll them all, and we sum them up. Let's probably end up with a total of k. Well, these are how many we could sum, and it starts at 0. And then that's probably the sum of these j draws add up to k, right? So that's fair enough. So we can do this part, right? So we could have 3 rolls, 4 rolls, 5 rolls, and if we have 3 rolls, then they have to add up to k. And so there are different ways of doing this, but this is sort of writing out in a big, nasty fashion. Okay, so we're going to replace those words with an actual expression. So we want the first one. So there's I1 through ij, right? There are j things. So these subscripts 1 to 3. So if we have, if we get a 7, then this will be I1 through I7, and that just means we've got 7 of these. So we multiply the probabilities of those together, and we want that these numbers are such that we get a set of numbers such that they add up to k. That's what this is, right? So this set I1 through ij, that's a such that we sum of this providing us k. So we want all of those possible permutations. or arrangements. And so if we think about the generating function, because this is a true statement, but we were interested in generating functions. So again, that's going to be, of course, just wk, x to the k. We're just wrapping the right things around it. So we're going to take this big statement and wrap our sum from k equals 0 at the front. This is all of this blob, and then we'll put an x to the k at the end. Just do it. Okay. And then we'll do some things. We're allowed to do this. It's not so bad, right? There are often some beautiful things you do with change of sums, but it's k equals 0 to infinity, j equals 0 to infinity. We go shloop. And this is, the j only appears here, right? There's nothing involved with this. Okay. And the reason we're trying to do that is we kind of know where we're going. This is starting to look like, if this is something to the j, if this blob here is something to the power of j, then it will look like a generating function, right? If it's x to the j, then that's a generating function for u. But if it's, banana to the j, then it's the generating function evaluated at banana, right? Okay. So we can kind of play around with this a little more with the fun times. Okay, so we've got x to the power of k over here. We have this condition, right? We need these things to sum up to k. So we can take this x to the k and spread it out. X to the I1, x to the I2, x to the ij. All of those things sum up to k. So that's starting to look like, these are starting to look like bits of the generating function for v, right? This is v7 x to the 7, which is the essence of a generating function for v. So we have to think about what these sums are doing. I think I will repeat it on the next one. Okay. And this is just the last slide. I think we'll get to that. Okay, so we've still got true statements here. This is still this is everything that was on the last line of the previous slide. And then we sort of look at this thing and think, oh, this is, not obviously, but we stare at this a little bit, and we see that this is x, the blob times x to the k that's sitting in this expression. So, this takes a little bit of thinking, but right, this is the generating function for v. So if we look at this thing, we're going to have this to the power of j, and this thing here, such that this is equal to k, must be that it's the x to the k power of this, this generating function times itself, j times. Because if we do that, we get every way we can get x to the blob, x to the blob, x to the blob, x to the blob, such that they all sum up to k. We pick out all of those pieces. Right? There's going to make a horrible mess. There's going to be just the zero parts. So there'll be a constant. There'll be everything that's multiplied x, everything multiplied squared, everything's going to come out of this. And because there's just such a free expression here, right? This is the way to get away. So that takes a little looking at. And this is a right. So this thing is the generating function of v power of j. Let me get it right. This is the x to the k piece. Now we're going to sum from k equals 0 to infinity. X to the k piece. So then that is right. That this unbraced goes to here. So that's the generating function for v power of power. Yep. Slow. Right. So everything collapses down. We've got a uj and then this blob to the power of j. Right. So this is a laborious way to go through it. You may have to look at it a few times. The piece that I think I give you in your assignment it tells the story in a better way. But ultimately we get this result, fu fv of x. So this means that we're doing right? I mean, look at this. This is a horrible thing to do. I mean, it shows you the guts of the calculation in here, but this is a much cleaner story. If we're working in generating function space, then just do it really easily. Yeah. We still have to undo the generating function, but it's really easy to do. Okay. Okay, so, yeah, as I said, that proof is groovier. All right, that's good. So ask a question. Yep.
Are we always trying to get it in that form of whatever u, v, x to the I, whenever we're trying to make these generated functions?
Yeah, you need to be able to see, right, because this is the fundamental structure. It's going to be, blob to the j, uj, sum over that. We've got to get there somehow. We got part of this way, right? This is the x to the k piece of this thing. And then we sum over k equals 0 to infinity. Right? And then we've really, because we're summing over k equals 0 to infinity, then we really actually have the generating function.
We're just trying to regroup everything in terms of like something x to the something.
Yes. And those indices have to match. They have to match. You have to use. So you go, yeah, you just bash everything to pieces until you end up with probability, sub whatever it is, astronaut, blob to the power of astronaut. That's fine. Yeah. So there's, I think, a better way to do it in your assignments, but I wanted to give you a slightly disconcerting way to do it. I think that's good. So as I said, we're going to be back on Tuesday.